Number 7, we have 9 parts. It says the reading speed of second grade students in a large city is approximately normal with a mean of 92 and a standard deviation of 10. We're going to complete parts A through F. So what is the probability a randomly selected student will read more than 97 words per minute? So StatCrunch, more than 97 words per minute. We are going to go to Stat, Calculators, Normal, Standard. We're going to do greater than. We are going to use our mean of 92. Standard deviation was 10. And we want greater than 97, more than 97. Alright, so that gives us 30.85, 4 decimal places, 0.3085. If we did this 100 times, so I'll multiply this times 100, that looks like 31. And so in the previous problem, it told us to round to the nearest whole number. So we're going to continue that practice. So we're going to round, instead of 30.85, we're going to round to 31. And we're looking for more than. That says less than, exactly, and this one says more than. Since our original problem wanted read that or more. So we're going to say we would expect 31 to read 97 or more. Part B, what's the probability that a random sample of 14 will result in a mean of more than 97? So now we're applying the normal approximation. So our standard deviation, the difference here, our standard deviation is changing to sigma over the square root of n. And so I'm going to put that in to StatCrunch, and then I'll leave everything else the same. So my standard deviation, which was 10, I'm going to divide that by a sample of size 14. Divide by, and I'm going to do SQRT, and then 14. How do I know I can use this? Well, because they told me that it was approximately normal, so it's coming from a normal distribution. So even though this 14 is not 30 or bigger, we can use normal because the distribution was already normal. All right, so it's still greater than 97. We're going to compute, and we get 0.0307 when rounded, 0.0307. If we did this 100 times, so I'll multiply this probability times 100, and that gives us roughly 3, rounded to a whole number. And we want it more, so B, roughly 3 from that sample. And then part C, what's the probability that a random sample of 28 would result in reading more than 97 words per minute? So our sample size has changed. So I'm just going to come over here, change our sample size from 14 to 28. And then my probability goes smaller, so 0.0041 when rounded, 0.0041. If we did this times 100, that would not round up to a whole number, so that would just be 0 would read more than 97. So A, looking at 0, reading more. What effect does increasing the sample size have on the probability? So as we look at these examples. So part B, we had a sample size of 14. Probability was 0.03. When we increased the sample size to 28, our probability went down to 0.004. So increasing the sample size caused my probability to go down. So that's what this is asking. What effect does increasing the sample size have on the probability? Increasing the sample size decreases the probability because sigma decreases as n increases. Increasing the sample size decreases the probability because sigma increases as n increases. So let's look at what happens to sigma. I believe it's A, but let's look at the sigma. So if I take the 10, which is my standard deviation, divided by the square root of 14, that was my first sample size, we get this. So this is my sigma x. If I do 10 divided by square root of 28 this time, my sigma decrease. So as the sample size increases, my sigma is decreasing, and so my probability. So increasing the sample size decreases the probability because as sigma decreases, it decreases as n increases. So A, that's what we notice is happening. E, teacher instituted a new reading program at the school after 10 weeks. In the program, it was found that the mean reading speed of a sample of 19 was 94.8. What might we conclude based on these results? We're going to select the choice that best explains, and we're going to fill in the boxes. So we have two options. A mean reading rate of 94 is not unusual since the probability of obtaining a result is more than blank. This means that we would expect the mean reading rate of 94 or higher for a population who has a mean of 92 out of every 100 samples of size 19. The new program is not abundantly more effective than the old, and then this one says the reading rate is unusual. So first we need to find the probability. If it's greater than 5%, it would be okay. If it was less than 5, it would be unusual. So we first need to compute the probability. So we're still using the original mean. Standard deviation, we have samples of size 19. So I'm going to come here. I'm going to change this to a sample size of 19. And from this reading said that the reading program found that the mean speed of a sample was 94.8. So this says obtaining a result of 98 or more, and this one also says or more. So I want to find what's the chance that we would be 94.8 or more. So change this to 94.8 or higher. So from there we get 11%, 0.1111, and that will not round. So this is greater than 5%, so that means it is not unusual. So the probability of doing that or more is not unusual. So A is the one we want to go with, 0.1111. We would expect, if I multiply this by 100, because that's what this is, that would be about 11, and that will not round to a larger whole number. And then F, there is a 5% chance that the mean reading speed of a random sample of 23 students will exceed what value? So we are working backwards and we're trying to find the x value so that a sample of 23 will exceed 5%. So, or there's a 5% chance that it will exceed this number. So here's what we are looking at now. 7.9. We're told 5% chance that we will exceed this number. So I'm trying to find, so if my mean is 92 for my regular distribution, I'm looking for some number such that the area over here to the right is 0.05. Okay. So I'm going to work backwards. I have to find the z-score from the table that corresponds to 5% being the area to the right. Remember, z-table only tells me the area to the left, so I would be looking for a positive number such that the area to the left is 95%, because 95 and 5 is 100. The whole thing has to be 100. So from here all the way back, it's going to be 95. And so that's what I'm looking for in the table. 1 minus the area to the right is equal to the area to the left. So I need to be on the positive table. I'm looking for 95%. Getting bigger, so I'll probably want to be on this line. Okay, so 94 and then 95. It happens right between these two. If we look at which one is closer, this one ends in a 95, so if I added 5, it will round up to 95. This one's 05. If I subtract 5, I will have exactly 95. So neither of these numbers are closer. The 95 is like exactly in the middle. This only happens like a couple times in the table. So when it's exactly in the middle of two numbers, we have to find the average. So this is 1.6, 1.60, 1, 2, 3, 4, and 5. 1.64, 1.65. Okay, so this x value or the z value is 1.64 and 1.65. It's going to be halfway between those two. So if I add these and divide by 2, we get 1.645. So using the approximately normal z formula, we are saying x bar, which is what I'm looking for, minus the mean divided by the sigma over square root of n, and we're going to work backwards to find the z-score. So we got z, which is 1.645 equal to x bar minus the mean of 92 divided by standard deviation of, what was that, 10 over square root of, our sample size was 23. Alright, so we're going to multiply, work backwards by the denominator to get this fraction going. Times 10 over square root of 23, and that's going to be equal to x bar minus 92, and then we're going to add the 92 to get the x bar by itself, and that will find our value. So 1.645 times 10 over square root of 92, sorry, 23. Plus 92 equals the x bar. So this is a little bit of algebra working backwards. This is how we find our threshold for this x value here. So 1.645 times 10 divided by the square root of 23, and then plus 92. So 95.43 would be our threshold.